All right. Hello, everyone. This is MASA-Dearborn, and this is our podium session with our deployable fins system, and our rocket's name is Boosted Bear, the next generation. So the purpose of the deployable fins as a system is to allow for a more efficient flight in the 30,000 K category. So our team wanted to experiment with the new solutions to prevent previous problems with such a system, and I will talk about these in a little bit. But the purpose of the deployable fins is to stabilize the rocket during the second stage, and the bottom bulkhead, which is also part of this system, serves as a stiff mounting platform for the threaded rods, which support the structure of the rocket. So it's an important structural element as well. And it's obviously a mounting platform for the fins. Right. So here are some of our previous design iterations. So in 2017, 2018, we had dart fins that were similar downward opening fins. After that, we had wraparound fins, and last year we had deployable fins, which opening upward, so into the airstream. None of these designs were without issues. So in 2017, 2018, we had rigidity issues. After that, the wraparound fins were very difficult to manufacture. And last year, we had to use very strong springs because we are opening into the airstream. And we had to be careful in well, we didn't succeed in making it because of COVID, but it would have been very dangerous to assemble, and it would have needed special tools. So this is this year's system. As you can see, system side view and system exploded view. So the design changes that we made were these T-bars, which are the red component, as you can see here. And those are included to increase rigidity. So the 2017-2018 rocket showed rigidity issues, which we believe are to a degree inherent with a downward opening fin configuration, because there is a lot of empty space, and there is just isn't as much hardware in this configuration as with other configurations. So this new T-bar feature increased rigidity by 76% while still being 37% lighter at 2.9 pounds than last year's upward opening deployable fins. And the braces are held in place with the spiral vent-out dowel pins connected to both the top and bottom bulkheads. So those are the pins which you can see here. And once assembled, the system can be slid out from the flight package for quick serviceability. The separation sensor, which is also a component of this system, is ported to the top bulkhead. And the reason for these holes, which you can see on the picture here, is so that a wire connecting the separation sensor to other systems can be threaded through these holes and down that rectangular hole, which you can see there. So it can communicate. We can communicate with the rest of the rocket so that the systems are aware that separation has happened. And here you can also see those holes. So in order to take full advantage of the T-profile, the system is designed to always be in compression, pulled tight by the threaded rods. And the threaded rods are essentially steel rods which pull the system in compression and also other systems on top of it. And they are essential to the structural integrity of the rocket. And the dowel pins are only there for safety. So since it's always supposed to be in compression, there is never supposed to be a situation where it's only the dowel pins holding in the T-bar. The body tube is designed to sit on this little edge you can see on the picture on the right. and is expected to be cut in a way where it's either a slight press or a small gap between the bottom of the body tube and the bottom bulkhead. The fin holder arms are not in compression by the shoulder screw, which you can see. This shoulder screw is basically the axis of rotation for the fin, and the fin holder arms are not in compression because the shoulder of the shoulder screw actually rests on the left fin holder arm. So the only sort of compression is between the nut, which is orange, and the shoulder of the shoulder screw, which is inside the left fin holder nut. That's why it's the left fin holder arm. That's why it's a little thicker. Right. And the fin holder nut has a plastic orange insert to prevent loosening from any sort of vibration. And the report includes more integration details. All right. So regarding manufacturing, obviously this is the top and bottom bulkheads. Mainly the bottom is quite a complex geometry. So our team worked closely with the university's manufacturing laboratory staff to root out any issues. And the top and bottom bulkheads and also the fins will be CNC'd. And the aluminum braces, which I've seen before, will be cut to size on the saw and manual mill. The base and braces will be drilled through simultaneously after assembly on the rotary cutter to ensure proper hole alignment. So because obviously it has to be a tight fit. The holes for fin axis will also be cut on the rotary cutter, and all manual cuts have zeroing surfaces, as they should. Right here you can see the engineering drawings. These are so we have drawings for every single manual cut. So whatever is not on the CNC, not done on the CNC, receives a drawing. All right. So our analysis included hand calculations and also SolidWorks simulations, as well as CFD simulations. So we considered all sorts of failure points. So bearing failure in the T-bars, T-rod failure of the T-bars, bearing failure in the fin, shear in the shoulder screw that holds the fin. So various issues, and they were all found to be negligible. Mainly, the one that was a concern is shear in the and or bearing failure in the around the fin, and that was found to be negligible as well. The only reason why we didn't decrease the shoulder screw diameter even more is because it also acts as a mounting platform for the spring. All right. So the spring strength was selected to be 3 pound-inches. I'm sorry, 3.1 pound-inches at an opening angle of 180 degrees. And this selection was done based on previous designs, and also was verified further with the drag force equation with very conservative values for velocity and also for drag coefficient. You can find more details about this in the report. We had a 0.07 second fin opening time, that is assuming no friction, and we had a 1 degree angle of attack shift during opening using OpenRocket, which was calculated using OpenRocket. The brace and the threaded rods failed simultaneously, as they should. Right. So the brace is a wait, what's here? Brace is stronger, but it's going to be 16 inches instead of 18. That's going to be as much rigidity. Oh, right. So we considered going with a thinner T-bar. However, it would introduce buckling concerns, and it was also much too thin. And well, also buckling concerns and also tear out issues, which are not a concern in the thicker version. We also completed fin flutter analysis which revealed no rigidity issues. I should also include that regarding fin flutter analysis, we did not consider any sort of gap between the fin holder arms and the fin itself. So we assumed that it was just one component, because if we actually modeled that as a joint, that would have significantly complicated analysis. The optimal torque to tighten down the threaded rods is what was determined to be 37 inch-pounds to 59 inch-pounds, which comes from modeling the system as a joint, so a bolt and member, in which case the bolt would be the threaded rods and the member would be the T-bars. So this optimal torque was determined so that the threaded rods yield at the same point, under the same bending moment as the T-bars become or go under compression. So here on the bottom of the picture, you can see that hole which would house one threaded rods. At the moment that threaded rods yields in compression, that's the exact same moment when the T-bar in the opposite side becomes in tension. Right. All right. So our analysis also included CFD simulations, and it was mainly concerned with the impact of air brakes on the stability of the rocket. So since this is the first year we have tried an air brake, tried to include an air brake system, we have spent a considerable amount of time to eliminate any sort of issues. So there was two approaches to this analysis. The first direction was done through open rocket, which showed a negligible improvement on the average stability of the rocket by 0.03 calibers when the air brakes are fully open. And the second approach was CFD simulations, which showed that the turbulent wakes from the air brakes do not reach the fins for either low or high velocities and at different angle of attacks. So we concluded that the effects of the air brakes on rocket stability can safely be ignored. All right, so here you can see this is a different illustration. So here it is velocity and pressure along the surface of the rocket. You can see that the wakes do not reach the deployable fins. And here's another view where you can see velocity on the surface of the rocket like previously, but the pressure is actually a slice. So you can see that after on a layer that's after the rocket, that's the illustration on the right, and on the left you can see that similar layer, pressure layer, right before the air hits the fins. So you can see that the wake is not present there. So there should be no issues of pressure wakes hitting the fins. And now on to flight simulations, which will be presented by Sarah Dormo.
Hi, I'll be talking briefly about flight analysis. So with our current design of the deployable fins and the air brakes, we have a predicted flight with an apogee of about 10,100 feet. That number is somewhat estimated because our open rocket does not model air brakes very properly, so that is unfortunate there. But our max velocity is 787 feet per second. Our max acceleration is 183 feet per second squared. So the fins deploy just after separation, which occurs about 12.4 seconds and about an altitude of 8,000 feet. Over here is just a graph that depicts the altitude, vertical velocity, vertical acceleration, with the altitude splitting for the two bodies. Next slide. Okay, so the fins after separation are the only thing that is providing stability to the rocket, specifically the dart. And the graph on the right depicts flight stability from separation to apogee, which is the only time that the deployable fins are deployed. And so I looked at the stability here, and it's about 1.9 to 1.65 as a low and a high. So the maximum difference is only about 0.35, which is fairly small, and only really occurs when the rocket is reaching apogee and slowing down, which it makes sense. The stability of the rocket would go lower would decrease as it slows down in the air and reaches free fall. So the deployable fins we have concluded provide very stable flight to the dart after separation to apogee. And this over here is just a graph depicting the stability, with the red line depicting the stability of the dart after apogee. And then we'll be moving on to questions. Next thing.
One thing before we move to questions, Barnabas and Sarah, would you like to clarify the method of estimation for that apogee? Because it wasn't just like we just guessed, but you guys did use a method to find that number.
We just used some simple projectile motion equations, assuming that deceleration caused by the air brakes was constant. So that's how we got that 10,100 feet-ish.
Right. It was also, I should clarify, it was a combination from, input from a different types of softwares. So with OpenRocket, we calculated what conditions would occur at separation, so altitude, velocity, orientation, etc. We also did a number of CFD simulations to generate a drag force data table for the air brakes, which was a very extensive investigation that you can read more about in the report. But using that data, we generated an average value that should model relatively well how, when plugged into projectile motion equations, how the rocket how high the rocket will go. So that was our process. Yep. And now on to questions.
So thank you. So if there are questions, those attending, please go ahead and type them into the chat window. If you want to use the Q&A tab, that's great, or just the plain chat would be fine too. I've got a question for you. Maybe you can talk a little bit about your materials selections. What different types of materials did you consider, and how did you make a final decision on what the best material to use was?
Of course. Yeah, that's actually a very good question. So the let me click to exit. Let me go back and show the system here. So regarding the fins, the bottom bulkhead and the top bulkhead, those are all made out of 6061 aluminum. The reason for that selection was, it was several reasons. One is 6061 aluminum provides excellent resistance to impact. So that's good for the fins, obviously. Another reason why is that it was affordable with the university's budget cuts this semester, or this year rather. It's been challenging to make design decisions that will allow us to manufacture this rocket successfully. If the manufacturing will take place in the future, I should clarify that. But so that's how we that was included in the design. The last thing was manufacturing concerns. So obviously, with this complicated geometry of the top and bottom bulkhead, we want to be able to manufacture fast. So the cam picture that you have seen, that illustration, if I remember correct, that would have taken about 6 hours to manufacture. With a harder type of aluminum, that would have been longer. Regarding the braces, we have selected 2024 aluminum because of its excellent strength to weight ratio and stiffness to weight ratio rather. Regarding the pins, those are made of 4041 alloy steel, which are it's a tool steel, so it's very resistant to any sort of loading or that sort of things.
Mm-hmm. Okay.
Another reason we use aluminum is also weight reduction, since this is in the center of our vehicle, and we want to make sure that we stabilize the vehicle with mass in the forward section of the vehicle, in the payload. So we want to reduce mass in this center area so we don't have to add more mass up in the nose cone.
Okay. Sure. Mm-hmm. Just curious if you did. It looks like in this diagram, I'm just looking at the screws and fasteners and things like that. If there was any decisions to standardize on some of the ways that you'll assemble this, same types of screws or fasteners, things like that, kind of throughout, or is it all different?
Right. So. Whenever possible, yes. Regarding so since the team is organized in a way where everyone has their own sections or systems they are in charge of designing, we do have some variation of parts. However, whenever possible, we try to have interchangeability.
Sure. Okay, good. There was one question in chat about if you have a video or the image sequence of the fins deploying.
Oh, thank you for calling my attention to that. No. So with the manufacturing process, well, with any sort of manufacturing equipment being unavailable to us, we do not have the these items manufactured yet. What we do have is some 3D printed components, which we aim to use for testing as soon as university allows for purchasing.
Okay.
So we haven't been allowed to purchase these things officially, but so it has been up to our members to kind of find ways to manufacture some of these components in-house if they can, which is obviously very challenging for things that have to be CNC'd.
Right. Yeah, let's see. I was thinking about the materials and then also vibration and maybe shock. Do you account for that? And or is it strictly aerodynamic forces that you're accounting for?
Right. So all nuts are made with plastic inserts. So that's what we believed would be a good idea to do against vibrations. And also the reason for the holes on the left picture is so that the wire would be threaded through it for the separation sensor, like I mentioned. So that is if the fins wobble from side to side, perhaps, or maybe the wire could become tangled or something. So that's that was also a consideration. But regarding vibration simulations, we haven't investigated that portion of the project.
Okay.
But we do plan on looking into that with like when we can access physical testing and stuff like that.
Yes, I should have mentioned that. Yes, so once physical testing is available, we do plan to. Well, there's a variety of tests. So there will be a temperature test. There will also be a vibration test. There will be a drop test to make sure that the fins open reliably.
Right. Okay. Very good. Yeah, that was one of the questions about that. Concerns of them getting stuck, and any concerns with manufacturing and assembly, in particular.
Right. I'm looking at the questions. I can only see some of these, but Oh yeah,
In
any
the
major
chat
difficulties
overview.
with manufacturing assembly. Right. So that was an important design consideration. So the hardest part or the most challenging part of manufacturing and assembly for that regard is proper mounting of these pins with the T-bars, right? So because there can be no gap. So we made the decision so that those holes will only be drilled once both the top and bottom bulkhead geometry is cut, and then the entire system will be placed in the rotary cutter, held tight by the threaded rods, and then that way we can precisely drill those holes at the exact size we need, at the exact location we need, and then we can just put in the pins. So that was a major issue, but we have also designed this to be kind of modular, so the whole system can be slid out and slid back into the rocket as a whole.
Very good, very good. Well, I do want to keep track of time, and there's some other events I need to go make sure they're happening. So I'll thank you very much for your presentation. I know there's a few other questions in chat. You can answer those offline, but I will stop the broadcast here, and thank you very much.